this video we're going to discuss some technical details about this confidence interval procedure, and we just wanted to make sure that's clear. You don't have to know this material most often in elementary stats class. It's not even mentioned, but I just thought it would be appropriate to mention it. So we're going to talk about what we're actually trying to estimate. We want to try to estimate this quantity, the mean for the population for the first population, minus the mean for the second population. We're trying to figure out the difference between those two means. That's what we're trying to do when we form this confidence interval procedure. So the first thing you want to think of is, well, how would you estimate that? What would you use? And a good logical choice might be to choose x bar 1 minus x bar 2. So that makes sense to me because a good point estimator for the first population mean is x bar 1. A good point estimator for the second population mean is x bar 2. Now when I say a good point estimator, I mean that these guys are unbiased, right? They also turn out to have the minimum variance of all the unbiased estimators that are out there. So let's focus on the unbiased part though. Unbiased means that the average value for x bar 1 should be the mean for population 1, and the average value for x bar 2 should be the mean for population 2. In other words, what I'm saying is that the expected value for x bar 1 should be mu 1, and the same should be true for x bar 2 and mu 2. So that's a really nice property, and so we want to see now what's the expected value for this quantity. We would like it to be this thing. Is the expected value for this quantity what we expect? Is it this quantity here? So our question mark here is essentially, is this going to turn out to be this? And in order to answer that, we have to look at a property of expectation. So let's just look at that property very quickly. The property of expectation is this. It turns out that the expected value of x plus y can be shown to be the expected value of x plus the expected value of y. In other words, we can simply say that the expected value of the sum of two random variables is the sum of their expectations. So what's really nice about this is if we substitute for x and y our x bar 1 and our x bar 2, right? Because basically that's what we have here. So if I just change this part here, x bar 1 and 2, x bar 1, and let's make it minus x bar 2, then this expression here would turn out to be minus between them, and we'll have x bar 1, x bar 2 in place. And then, because we said that the expectation here for x bar 1 is just mu 1, and the expectation for this is just mu 2, then it turns out that the expected value for this quantity is in fact the thing we'd like it to be. So it means that this estimator here is an unbiased estimator of mu 1 minus mu 2, and that's great. Okay, so that's one of the reasons why we use this quantity to estimate that item. The other reason why it's important is that it turns out it'll be the minimum variance estimator of that as well. All right, well let's go on though from there and talk about if we choose this as our estimator, we need to know its standard error, because in that confidence interval procedure, we rely on the margin of error, which has the standard error as part of it. So if you remember, our formula for margin of error turned out to be z alpha divided by 2 times this quantity, right? And this quantity we call the standard error. That's the standard error of our estimator, x bar 1 minus x bar 2. The question is this in fact the standard error, and if so, why? Okay, well it is the standard error. Let's show why it's the standard error. Well, if you're trying to calculate the standard error, that's this guy for x bar 1 minus x bar 2. If you want to know the standard error for that, it turns out that that'll be equal to the square root of the variance for x bar 1 minus x bar 2. So we need to figure out then what is the variance for x bar 1 minus x bar 2, and then take the square root of it. Well, we can actually do that by using a special property. Let's first talk about an individual thing. Do we know the variance of x bar 1? Of course, we know that we know the variance for x bar 2 also, because it's basically the same thing, right? The subscript of 2. But do we know the variance of x bar 1? We actually do, because we know that according to the central limit theorem, x bar is normally distributed, right, as long as the sample size is large enough, with mean, mu, standard deviation, sigma over the square root of n. We would have learned that back before when we learned the central limit theorem. So So this is true if you square this, because we're dealing with the variance and not the standard deviation. So again, we would have learned that the standard deviation was sigma over the square root of n. To get the variance, we just square that quantity. So of course we know that that becomes sigma 1 squared over n. So we do know the variance of x bar 1 because of the central limit theorem. And by the way, central limit theorem, this part of it doesn't depend upon normality, right? This is the variance for x bar 1, regardless of whether it's normally distributed or not, right? Okay, so either way, we know the variance for x bar 1. Fine. Of course, we also know the variance for x bar 2. Just put 2's here for that subscript, and you have that. Of course, the n here is also subscript 1, right? All right, either way, so we know the variance for x bar 1. We also know the variance for x bar 2. But do we know the variance for the difference between these two quantities? Well, in order to know that, we have to look at a property. Turns out there's a property of variance that says this. You have the variance of x plus y. It's equal to the variance of x plus the variance of y plus 2 times the covariance of x and y. Now, this part here, this 2 times the covariance, I doubt you would have seen that in your elementary stats class. Most professors do not discuss this in elementary statistics. But what we can say is that we don't have to worry about it as long as these two variables are independent. Because it turns out if x and y are independent, if they're from two independent populations, like in our example we talked about comparing male test scores to female test scores, those are two independent groups that don't rely on one another. So if we were to say that those two groups are truly independent, it turns out the covariance is 0. So we don't have to worry about that term. It drops away and we can just ignore it. So let's assume that x and y are independent, which is the assumption for this section. Then at that point, we just need to add the two variances together to get the variance for x plus y. Well, in our case, we don't have x plus y. Instead, we have what? We have x bar 1 minus x bar 2. That's okay. We just change this statement then to this. The variance for x bar 1 minus the variance for x bar 2. That's all we have to do, right? Straight across just like that. And then we just have to know these quantities, which we said we knew. So we actually do know those. The variance of x bar 1 is sigma squared 1 divided by n sub 1 plus sigma squared for population 2 divided by n sub 2. So that's the variance. And then of course, if that's the variance for this quantity, that's what we put under the square root symbol. And now we have our answer for the standard error for x bar 1 minus x bar 2. It is the square root of sigma squared for population 1 over n1 plus sigma squared for population 2 over n2. And that's finally your standard error for the estimator. So it's complicated. There's a lot of mathematics here, a lot of theory, and of course, some of it's outside the scope of the course, so we have to kind of almost talk about things that we haven't yet learned. But it's just if you wanted to know the technical details, you wanted to see that there is support for our choices of the standard error, for our choice of the point estimator x bar 1 minus x bar 2. We do have that support. There is theoretical underpinnings for all this